Okay, so this question here, we see a woodpecker's brain is protected from high acceleration, right? And the woodpecker is a bird that creates holes in trees using its beak. Uh, and thus, large forces, right? So its brain is also protected from large forces by tendon-like attachments inside its skull. Okay, so while pecking on a tree, the woodpecker's head comes to a stop from an initial speed of 0.54 meter per second. So we have to define our parameter. We have to set our set up our problem. So V naught here equals to 0.54 meter per second. All right, and it comes to a stop, meaning that its final velocity v is 0. Okay, now in a distance, so the woodpecker's head traveled the woodpecker's head here traveled a distance of 2.4 millimeter, so that is x. All right, x equals to 2.4 millimeter. So since it traveled a distance of that, it means our change in x, which is what? Which is our x minus x naught, is actually 2.44. So we can just put that change in x, which is x minus x naught, right, is equal to 2.44 millimeter. Now, of course, we're looking at it, we can't work with this. Velocity is in meter per second, distance in millimeter, so we have to convert this. So this would be equal to 2.4 divided by 1000, right, which is equal to 0.0024. So we have defined our parameters here. Okay, let's look at what they what they need from us here. So assuming constant acceleration, when we see that, of course, we should use our equations for constant acceleration. Find the magnitude of its head's acceleration in multiples of g, and we are given the value for g. So we need to find acceleration. So that's what is needed here. Okay, now that we've defined our parameter, we need to choose the equation of motion that would where we'll be able to use these parameters and be able to get our acceleration. So that the best one here is going to be v squared equals to v naught squared plus 2a x minus x naught. All right, that's distance traveled. So we already have that already to be the head traveled a distance of 0.0024. So let's put in our values. Our final velocity is 0. 0 squared is still 0, so 0. Our initial velocity is 0.54 meter per second. So 0.54 squared plus 2 times a times 0.0024. Okay, now let's do some quick algebra. We have negative 0.54 squared equals to, right, if we multiply that, we should have about 0.0048 a. So we divide both sides by 0.0048. So when we do that, we have that our acceleration is negative 112.5 meter per second squared. Our acceleration is negative. Of course, it should be negative because, of course, we see that the head comes to a stop here, right? The head comes to a stop, meaning that what we are calculating was our actually our acceleration in the backward direction, right? So anytime the final velocity is is negative, we usually get a negative. We're usually going to calculate a negative acceleration. Not that it affects the magnitude, but of course it shows the direction of the acceleration. But they asked us here for the magnitude. Okay, so we need to calculate the stopping time of the woodpecker's head. Okay, so of course we have our parameters, but now we need to find time. So the best formula to use here in this case is going to be x minus x naught equals to u plus v. In this case, u is v naught. Okay, let's specify that v naught plus v divided by 2 times time. All right, we already have our x minus x naught to be 0.0024. All right, equals to our v naught is 0.54. Our final velocity there was 0, as we've earlier defined, but of course it's 0, it has no effect on that, so we just divide by 2 and multiply by time. All right, so 0.54 divided by 2 is equal to 0.27 times time. So in this case here, what we are going to do is we are dividing by 0.27, both sides by 0.27 here. All right, so we have that our time is going to be 0.0089 seconds. Of course, if you've seen a woodpecker move, it's usually very fast. So this is actually an accurate representation of the woodpecker's movement. All right. The tendons cradling the woodpecker's brain stretch, right, making the stopping distance to be 4.3 millimeter. Now you're talking about the woodpecker's brain now. So you're told that the woodpecker's brain travels a distance different from the head, right, for safety reasons. So we can put that xb equals to 4.3 millimeter. Of course, since we're dealing with meter, we need to express it as meter. So 4.3 millimeter divided by 1000. We have about 0.0043 meter, right? So the woodpecker's brain traveled for this distance. Of course, since we can express our initial position to be 0, and therefore calculate the change in distance, or in this case xb minus xb naught, right, to be equal to 0.0043 meter. Okay, now that results in a lower magnitude of acceleration for the brain. So the brain has a reduced acceleration. All right, the brain has a reduced acceleration. Okay, what's the magnitude of the brain's acceleration? Now we need to find its magnitude there. So we can use the same formula we use to find the magnitude of acceleration for the head, which is v squared equals to v naught squared plus 2 times a times change in position. So in this case here, our v our v, because it stops, is going to be 0. Our v naught is going to be it still traveled with the same velocity, 0.54 squared equals to 2 times acceleration, which we need to find, times the change in position there. All right. Oh, that is a positive. All right. So we can subtract 0.54 squared from both sides. All right. So 2 times 0.0043 gives us about 0.0086. Divide both sides by that. Now A will be equal to 33.9 meter per second squared. Now we are doing this in terms of G. Oh, negative, right? But of course we are looking for its magnitude, so we do not need to include that in the answer. So we're dividing it by 9.8 meter per second squared, which is the value we are given for G. So acceleration for the brain, okay, we can specify that in our calculation. Acceleration for the brain is equal to 3.5 G. 3.5 G. Now we can see that it is quite lesser than the acceleration for the head, right? It's quite lesser, and that's because of the tendons. The tendons makes it to stretch. So instead of the head to cover that distance, right, the same distance as the same short distance as the head, rather it goes forward. So that force makes it cover a larger distance, therefore reducing its acceleration. Now the time of the journey is being elongated, right? The time of the journey is being elongated, and remember, acceleration is meter per second squared, meaning that the increase in time reduces the acceleration exponentially, right? It reduces the acceleration so much. So the head traveled a certain distance, right, in a certain amount of time. Now the brain traveled a distance too, but now moved for a larger amount of time, therefore reducing the acceleration of the brain.